literally peak like skill. Dude, are you kidding me? You're blowing into a tube. What? How does that have anything to do with bagpipes? But how do bagpipes?
I was associating one.
Oh.
No, yes, I think that's the fair.
I never said which name.
Yeah, exactly.
Oh, I'm sure once we get an answer.
It's all about language.
That sucker part of it. I think once we're able to import my
Instantly blends in right away.
does itself as an analyzer.
Well, that would be sick. Bro, honestly, actually, you know what? If we didn't fuck up the shop, 100%. They didn't give a fuck. Yeah, we checked, dude. We checked for KPI. Like, no. Okay, yeah, literally. Okay. I didn't get the phone out. Said we wanted a new China. Really?
He was also like,
yeah, exactly. Bro, Ukraine every other day is like, oh, no, Russia. No, seriously. Russia. It's like yeah, exactly. It's like Pakistan.
just asking for the logo. Yeah, and I think it's I'm fairly certain it's just
the same street that I went, huh?
Okay, good morning everyone. Good morning. Couple of quick comments before we begin. I have posted the problem statement for today's lecture in your Carmen page. Okay? And I hope to continue doing this as we solve problems so that you don't waste time copying down what I'm writing on the board. The solution that I am solving during the lecture will more or less be the same as what I'm posting on Carmen at the end of the day as well. Okay. The second thing is you have a homework due this week, Sunday night. After today's lecture, you should be in a position to solve the homeworks. One thing I want to mention is during the weekends, I may not be very quick in replying back to you. Okay, you can try. You may or may not get a reply. Friday I am available during office hours. I am available after class as well. I am available before class as well. 10 to 11 I have office hours on Zoom. Right after class, if you have questions, we keep our distance, but you ask me something, I'll be more than happy to answer. Okay, and then 4 to 6, I have office hours. This homework, you will particularly find it to be a little intimidating, but things will get better as we go forward. Okay? And the only reason is because we missed out on class on Monday due to it being a holiday. Otherwise, you would have had a much faster head start onto your homeworks. Right. Now we are going to go to the problem that I posted. In the process, you will see all the formulae that we have come across utilized in this problem. Okay, it's a nice problem. It's a problem. Please let me know if my voice is too loud. People in the back and so on. Everybody okay? Okay. Alright, so in this problem, I have a window pane. Okay, so this is a window pane. This is made of some material which will have a thermal conductivity. You typically want your window panes to have very low thermal conductivity so that the heat that is inside the room is not going to be transferred onto the outside, so that you maintain your room to be nice and cozy. Right? So that's one thing that we are trying to find out in this problem, and I'll list it out. This window pane has a thickness of 2 centimeters. One side of the window pane is exposed to the room, so I'm going to draw the room here. This is the interior side of the window pane. Okay, so this is interior side or interior surface. All variables related to the interior surface will be labeled with the subscript little I. Then I'm going to have the outside. Okay, so the outside surface of the window pane, all the variables related to that particular side will be labeled with the subscript of O. The top and the bottom, and this is of course a 3-dimensional body, we are looking at only 1-dimensional heat transfer so far. So for us, there is only heat transfer taking place in the x direction. So if I draw an axis here, y-axis, x-axis, z-axis coming out of the page, there is no heat transfer in the z direction. There is no heat transfer in the y direction, so I'm going to show them as insulated surfaces. There is only heat transfer so far with the tools that we have seen along the x direction. Okay. The window, I'm just going to draw it once again, you don't need to, I'm just going to mark 2 things. Okay, so I have the inside surface I and the outside surface O. The outer side of the inner surface is this guy. And this is open to the room. The outer side of the outer surface is open to the atmosphere, as you can see, outside surface or atmosphere. So this is the outer side of O. This is open to the atmosphere. Does this make sense to everybody? Okay. The inner side of the inner surface and the inner side of the outer surface will be interacting throughout the volume of the window. Okay. So the inner side of I inner side of O, which is this guy here. Okay, so they will be interacting through the volume of the and this is the window. This is the window pane. There is some ambient room air, stale air, which is interacting with the outer side of the inner surface. Okay, so I'm going to draw it this way. So if I draw a cloud, it means that there is some fluid present. Okay, then here we are told that T infinity subscript I is the temperature of the air within the room, and Hi is the heat transfer coefficient due to convection between the air inside the room and the outer side of the inner surface. Likewise, I'm going to have something here. This is ambient air or outside air at temperature T infinity O. Convection heat transfer coefficient HO. These are all values that are given to you. Later on we will make it our life's mission to compute how to find H. You are also told that the temperature of the room is the same as T infinity I. So okay, and then the outside temperature is the same as, or the surrounding temperature is the same as the temperature of outside air. Okay, so I'm going to call these as T surrounding I and T surrounding O. And this is surrounding O. Does this picture make sense to everybody? Now we are going to list the variables that are given in the problem and the things that we are supposed to find. Okay, so you are given T infinity I is equal to T surrounding I. This is given to you as 24 degrees Celsius. Always note, if you are given something in degrees Celsius, the first thing you do is convert that into Kelvin. Okay? Then T infinity out, which is the temperature of the surrounding air and also the large surroundings outside. This is given to you as 2 degrees Celsius. So it's like a cold winter day. Inside is a little nice and warm. Ti is the temperature of the inner surface of the window pane. Of window. And this is given to us as 17 degrees Celsius. Temperature of the outer surface of the window is T naught. We need to find T naught. This is the temperature of the outer surface of the window. All these details are given in the problem statement posted on Karman. Okay. The second thing I need to do is also find the thermal conductivity of the material of the window pane. I'm going to reduce the volume slightly. So find the thermal conductivity of the material of the window pane. So K of the window okay, this is thermal conductivity. Can everybody still hear me clearly? Yes, question.
Is Ti the temperature of the inner side of I, and To is what we're finding, which is the inner side of O?
No, outer side and inner side, in this case, they have the same temperature. We are going to assume that the thickness of the inner and the outer sides are the same, or pretty much very, very small. Okay, so that's a good point. When we talk about the temperature of the window surface, we are not going to distinguish between the inner side and the outer side of one of these surfaces. Okay? So we're going to assume it to be very, very thin. Of course, there is a certain thickness there, which means it has to have its own thermal conductivity. And then I'm going to have a layer of vacuum or whatever it is in between the two planes. We're going to see things of those, that kind as well later on. Yeah? Okay. So this problem kind of encompasses pretty much what we've been seeing so far. And I want to start off by, first of all, listing all the assumptions that I will employ in this problem. And I want you to do the same thing when you do your homework as well. Okay, so assumptions. And one more detail that's given to us is that the emissivity of the inner and the outer surfaces, so I'm going to call that as epsilon I, I'm going to write it here, epsilon O, epsilon I, these are the surface emissivities. They are told to be the same. It need not be the case. It's a value between 0 and 1. In this case, we are given that as 0.6. First assumption, temperature change is taking place only along the x direction, so the direction of heat transfer is along the x-axis only, so one-dimensional steady state conditions, because there is no mention of energy generation. Okay, there is no reactions taking place within the window. So steady state. If there is no mention of energy generation, steady state, and 1D, heat transfer. We're going to assume that all the surfaces, if there is no mention of the surface absorptivity, we're going to mention that all the surfaces are gray surfaces. Surface absorptivity is alpha for the outer surface and inner surface. We're going to assume them to be the same as the emissivity of the outer and the inner surfaces. So alpha O is epsilon O, alpha I is equal to epsilon I, gray surface. Third assumption, we're going to assume that the room is very large compared to the size of the window pane, and the outside is very large compared to the size of the window pane. Okay, so room is very large. And outside is very large. If the room is very large, then it implies that the irradiation, which is the net incident radiant flux onto the inner surface, can be given as sigma times T of the room to the power 4. Okay? This tells me that Gi, which is the incident radiant flux on the inner surface due to the room, is going to be sigma T surrounding I to the power 4. This is not the amount that is absorbed, this is just the net radiant flux, as you would have seen from last week's lecture. And this here implies the same thing but for the outside. So this is GO is sigma surrounding temperature of the outside to the power 4. And sigma is the Stefan-Boltzmann constant, where sigma is 5.67 10 to the power minus 8 watts per meter square Kelvin to the power 4. And now the last piece of information that we are given in this particular problem. Okay, so what I'm going to do is I'm going to keep these two panels up there all the way so that we can always refer back to these variables whenever we have any issues. The convective heat transfer coefficient for the air interacting with the inner surface and that for the outer surface are as follows. So let me write that information here. HI is 7 watts meter square Kelvin, and then HO is 20 watts meter square. This is given. This is also given. And because it's a gray surface, then I have alpha of the outside and alpha of the inside surfaces to be equal to 0.6, which is the emissivity. Alright. Let's tackle this one by one. I'm sure you're all familiar with drawing control surfaces on control volumes. But I'm going to assume that some of us may have to refresh our memories. And I'm going to walk you through that. Okay? Drawing control surfaces on control volumes is the same thing that you do for a mechanics problem, drawing free body diagrams. It is the exact analogy, but for thermal sciences. So let's do that for our problem. Now there are two choices. In the first choice, bear with me, in the first choice, I'm going to take the window. So this is the first choice. And here is a window. This is going to be my control volume. There is no energy stored, there is no energy generated because it is steady state. So steady state implies that E dot stored. Maybe I want to write it somewhere here. E dot generated is 0. It's common sense, right? There is no energy that is generated within the body because it's at steady state. Everything is fine and dandy inside. Okay? So this is E dot stored is 0. E dot generated is 0. I'm going to draw a control surface on this control volume. There are a couple of choices. I can draw a control surface that encompasses the entire control volume in the following manner. Does this make sense to everybody? Or I can also take these dotted lines and draw it within the control volume. It's completely different. Right, so bear with me for this one. When I draw this, here is what you have to mark. Top and bottom, nothing is going on. So we just not worry about it at all. On the left side and on the right side, you mark all the energy terms. There are no work transfers involved in this problem. So you mark all the energy terms that are either entering into the control surface or leaving the control surface. And this implies you're looking at the interaction of the outer side of the inner surface. Okay? So if I draw what are these energy interactions, the outer side is at a certain temperature, so it's going to emit some energy. So I'm going to call it as E suffix I. Okay, this is the energy or the radiant flux that is emitted by the outer side of the inner surface. What's the direction of heat transfer? Is it from left to right or right to left? What do you think?
Left to right.
Left to right. Why is that?
The temperature outside is significantly colder than the temperature inside, and assuming that there's any thermal conductivity in the pane, that will
Very good, very good.
indoors to outdoors.
But there is a small caveat here. If I have energy generation within the control volume, then I am completely at a loss on what the direction of heat transfer is going to be. Because it is possible that things inside can start getting hotter up, heated up, and then I can have the direction of heat transfer branching off within the window pane, within the control volume of the window pane. So in this problem, the saving grace for us is that I have steady state one-dimensional heat transfer. which means that I don't have any energy generation within the control volume. So as one of you mentioned, it's obviously going to be from the hotter room fluid passing through the window pane, going out to the atmosphere. Okay? So which means there is convective heat transfer from the room air onto the outer side of the inner surface. This is going to be Q convection high. There is also some radiant flux coming from the room. A portion of this is going to be absorbed. So if I say that the radiant flux coming from the room is Gi, then the portion that is absorbed, which is the quantity that will be trying to cross through the control surface, is alpha times Gi, or alpha I times Gi. Does this make sense to everybody? This is the portion that is absorbed. This is the net radiant flux from the surrounding. This is the net irradiation. And I do have exactly something similar to this happening on the outer side of the outer surface. There is going to be some energy emitted in the form of radiant flux. Notice that these are all supposed to be fluxes. So this is Q double prime. I will have to multiply it by the surface area projecting out of the board to get the total rate of heat transfer. This is a flux, this is a flux, this is a flux. Okay? Then I'm going to have E out. Obviously we know that the direction of heat transfer is from left to right because of what we just discussed, which means that the convection is going to take place from the outer surface to the atmospheric air. So the direction is going to be marked as Q double prime, convection, O. Large surroundings on the outside, so there is some radiant flux from the surroundings. GO, this is net radiant flux, or net irradiation, that is the same thing. Okay? Out of which only a portion is going to be absorbed by the surface, and I'm going to call it as alpha O G. This is the portion that is absorbed. Notice my arrows. I did not take this arrow and push it inside so that its tip is pointing into the control surface. I don't do that. Why don't I do that? Is because when I'm drawing all these arrows, these represent the interactions of the outer side of the inner surface with the surroundings. Does this make sense to everybody? When I draw these arrows here, because of the way the control surface has been drawn, these arrows represent the interactions of the outer side of the outer surface with the surroundings. Yes, sir.
So since we're assuming that the panes on either side are, say, like very, very thin, in this situation, would it necessarily matter?
It really doesn't, because I'm not interested in anything that is taking place here or anything that is taking place here because of the way I have drawn my control surface. But if I had to change it, then I would have to start worrying about conduction heat transfer, which is exactly what I'm going to be doing next. Okay? Yeah. Which is my next control volume. Okay? So same window pane. Just going to draw it a little bulky, just so that I can draw my dotted lines. Now, instead of drawing these dotted lines outside, somebody will say, hey, why don't you draw them inside? Right? Which is a completely valid thing to ask. Dotted lines indicate control surface drawn around the control volume. They represent the boundary of the control volume that you are considering, either the outer boundary or the inner boundary. Now if I start drawing my arrows, can somebody help me? And it's completely fine to say the wrong answer. If you say you don't know, that is also completely fine. All I want is some mode of interaction between the two of us, or between all of you and me.
Control surface?
So let's say that I'm talking about this control surface. What are the arrows that could be either going in or coming out? Take a guess. Yes. You can shout out your answer. That's completely fine.
Opposite of everything.
That's one answer. Okay, very good try.
Induction.
Conduction. Okay. Anything else?
Would what you have so far just be the same, and then you would add in the connection?
Can't do that, right? Because of the fact that when I'm drawing my control surface this way, I am looking only at the interaction of the inner side of the inner surface with the dotted lines. I am looking at the interaction between the inner side of the outer surface with the dotted lines. And we are going to say something very critical here, and I can completely understand the confusion that this might cause. We are going to ignore radiative heat transfer through the volume of the body, because of the fact that our surface is an opaque surface. So if a surface is opaque, radiation becomes a surface phenomenon. It does not penetrate through the volume of the body, which means that whatever radiative energy is induced within the volume is not going to reach the inner sides of the outer and inner surfaces. Okay, so radiation is a surface phenomenon for us. So there is no radiative heat transfer. If I draw a control volume like this, radiation is goodbye. Okay? Does this make sense to everybody? And this is because you consider it as an opaque surface. So there is not much radiation that is transmitted, and whatever radiant energy that is generated within the volume does not have enough juice to penetrate and reach the inner sides of the inner and the outer surfaces. Question?
So when you say opaque, you're referring only to the radiation transfer, not the actual appearance of the window.
Absolutely. We are just considering it to be a solid body. And solid bodies in general are defined as opaque bodies. An opaque meaning there is no transmitted radiant energy from the outside. So if I write, for example, GI, right? I want to write it somewhere here. It is just GI absorbed, GI reflected, no GI transmitted. And we decided last time that this portion that is reflected does not do anything to the thermal energy of the surface.
So you could still theoretically see through this window.
Absolutely. Yeah. Opaque doesn't mean that I have painted it in a darker color. Absolutely. Yeah. Could be as transparent as daylight. All right, fantastic. What do I draw though?
Another one of the energy terms, just the E sub I to account for transfer to the inner outer surface, and kind of lost on that terminology, and then a term for conductive flux.
I see. Okay, so we will just call conductive flux as Q double prime conductive. So which means that the first arrow that I have to draw is conduction heat transfer, that is starting from the inner side of the inner surface going into the volume, which means that I'm going to have an arrow that is hitting the control surface this way. I'm just going to show it this way. It's not an arrow coming from the outside. I should have drawn my body to be a little bigger. This is Q double prime conduction I. Now you see, if the window had a thickness, we would have had to include some thermal conductivity of the material of the window as well. Here I'm just assuming that the window thickness, the pane thickness is very small. I just have a block of, like ice or something. Essentially, that's what I'm saying. Then I'm going to have heat coming in. If heat comes in, it has to go out somewhere. It cannot stay inside. It's not a welcome guest. So if heat is coming in and I know that the direction of heat transfer is from left to right, this heat has to move out of the control surface. So it's going to go through here, and this is Q conduction out. There is no E dot stored, there is no E dot generated. Is there any convection? There is no convection inside, because I'm saying that whatever inside stuff is there, it's vacuum. Or just the material, the solid body. It's not vacuum, I'm sorry. It's a solid body. You cannot have heat transfer due to conduction through vacuum. This is just a solid body within, inside. There is no conduction heat transfer here. These are the only things that are taking place if I draw the control surface in the following manner. These are the only things that take place when I draw the control surface in the following manner. You see the difference? I'm not drawing conduction. You see the difference here? I'm not drawing convection. And I'm not including radiation heat transfer, even though it could be there. We are assuming it to be the way we are, as a surface phenomenon. So this is situation 1. Situation 2. I'm going to draw 2 more situations. And then we should be ready to solve it. Okay? So third situation and the fourth situation. In the third situation, rather than draw a control surface throughout the entire volume, here is what I'm going to do. Why can't I draw a control surface only on the inner surface? So something like this. Nothing precludes me from doing that, right? Nobody's stopping me so far. If I draw something like that on a surface, that's called as a surface energy balance, which means that there will be no volumetric phenomenon associated with this. Which means that there is no energy storage, there is no energy generation, even if there was some happening within the control volume. So this is called as a surface energy balance. Implies that E dot stored and E dot generated is 0, even if these were not 0 within the control volume. Okay? And now you will see what I am going to do. On the outer side of this control surface, I am going to have the same terms as number 1 there. So I am going to have an EI. I'm going to have a Q convection double prime I, and I'm going to have a portion of the outside room radiation absorbed by this side. So this is alpha I, GI, because these are interactions of the outer side of the inner surface with the room. This can get confusing very quickly. Keep things separate. When I'm looking at these lines here, I'm looking at the interaction of the outer side of the inner surface with the surroundings. If my lines are drawn this way, I'm looking at the interactions of the inner side of that particular surface. Which means if I come here and I want to draw an arrow here, what could that arrow be?
Q convection I.
Very nice. That's it. And you now see that whatever I have drawn in the first figure is the same as what I have drawn in the second figure on the left side. Which is what a couple of you are also mentioning. But I cannot draw it willy-nilly. I have to be careful in saying that because of this drawing and because of that drawing, there is an energy balance on the surface, and so the terms are equal to each other. Then I do the same thing on the outer surface. This is my window. This is my control surface. I have interactions of the outer side of the outer surface, so there is energy that is emitted. Then there is energy that is absorbed by it from the radiant flux of the surroundings. This is alpha O, GO. Outer surface of this window pane is hotter than the ambient fluid, so there is convective heat transfer. What's here?
Q double prime conductive outer, or O.
Q double prime conduction O pointing into the control surface. So these are my four situations. In many problems, the biggest issue is which of these should I draw? That is always the stumbling block. And this is exactly the same as asking for a dynamics problem, how do I start this problem? You have to exercise many options. I don't have an answer for you. You have to look at the problem as a global picture and then see, okay, which one is more useful to draw versus which one gives me the same information as the previous ones. And this comes through practice. There is no shortcut for these things. I apologize. Then all you do is start doing energy balance, which is very simple because we know the first law for heat transfer, and I'm going to write that down here, first law for ME45 pen from last class. E dot store, E dot in, E dot out, plus or minus E dot generated. These are all rate of energy transfer terms. Which means their units will be in watts. Whatever I draw on the control surface are flux terms, which means their units will be in watts per meter square. Okay? And I'm going to pull down, I want to keep this guy here, and I want to keep all of those, so let me do the following. Erase these and push this up. And you have these variables in front of you, so now I can get rid of them. So let me look at one. Okay. E dot n, all the terms that are coming into the control volume across the control surface. What are the E dot n terms? I'm going to have Q double prime convection I times the area on the inner surface. Then I'm going to have any other terms that are coming in, alpha I gi times the area. Please multiply by the area when you do the final heat transfer, energy transfer, balance. And the last one is alpha naught G naught times the area of the outer surface. And we are going to assume that AI and A naught are the same because there is no information given to me. E dot out, same idea. Take all the terms that go out. It's question. Yes, yes. Thank you. E dot out, same idea. Everything that goes out. Just clump them together, add them up, take them out of their misery. This is EI and E naught. AI, E naught. A naught, all the emissive fluxes that are emitted from the surface, both inner and the outer, and then convective heat transfer from the outer surface to the ambient, so Q double prime, convection O times the area. If I look at 2, very simple. Q conduction I is equal to Q conduction out. There is nothing else going on there. Times AI is Q double prime conduction out times A naught. I'm going to write 3 and 4 and then we'll start solving the problem. The math is the easiest part of the problem. Setting up the problem is the hardest part. For 3, or before I do 3, let me finish off 1. E dot stored, E dot in, E dot out, E dot generated. Always write this equation. Take your time taking off terms that don't make a difference. This is gone. This is gone. So this tells me that whatever energy is coming in is equal to whatever energy is going out. Now I'm going to take all of these guys and start expanding them using the equations that we've studied. So E dot in is equal to E dot out. Start with E dot in. The areas are all the same, so I can cancel off all of these areas, because when I do E dot in is equal to E dot out, these areas will cancel off on all sides. Does this make sense to everybody? Okay, and if you want, you can write it out and you'll end up having the same thing. So if I do this, Q convection, HI, no area, we just got rid of it. T infinity I minus Ti. Alpha I is the same as epsilon I, which is the same as, I'm going to say it as epsilon. Epsilon I times Gi, which was sigma T surface temperature to the power 4. Then alpha naught G naught, same idea. Alpha is the same as epsilon, so this is epsilon naught sigma